Okay, I think it's working now. So, yeah, sorry, I got a little bit started because I thought it was recording. The next example that I wanted to show you was the Laplace transform of sine of kt, which is this, and this is another thing. You don't have to worry about remembering it because it is in the table. Just remember that it's in the table. But this is the last entry out of the table that I'll check by doing the work for it. So, right. By definition, what would this be? This would be this integral, e to the negative st times the function in question. I do the integral of that from 0 to infinity. Of course, that means I'm going to need to know the antiderivative of this function. And if you remember, this is one of the harder ones that you would have done in Calc 2 by integration by parts. So I came prepared with this. I don't want to just tell you the answer because I want to walk through deriving it, but I'll walk through it maybe a little fast. We have e to the ax sine bx. I'm going to let u be the sine part and dv be the exponential part, which means, so du would be b cosine bx, and v would be the antiderivative of this, which is 1 over a e to the ax. So I do integration by parts. I've got u times v, which is this, minus the integral of v du, which is this. And now I'm looking at the integral of v du, hoping that I can do that. I see a constant that I can pull out. Other than that, I see an exponential times a cosine, which maybe I would like to do the same thing with. I'll do integration by parts again. I'll let u be the trig part and dv be the exponential part. This time du would be negative b sine bx, and v would be 1 over a e to the ax. And so I'm doing integration by parts to that. So what happens is I take this expression, I copy this down, I copy this constant down, and then I'm going to write in this set of parentheses, I'm writing the result of integration by parts on just this thing. In other words, I'm writing u times v, and it's this u and this v, not the stuff from before. It's this u and this v. So u times v is this, and then integral of v du is this. And now I can start to see something happening. I see the same type of integral that I started with. E to the ax sine bx. Whoops, and I guess this should have a dx on it, of course. Because this is the same as this that I started with, e to the ax sine bx. Same thing here and here. So this is, if you remember, hopefully this is ringing a bell now, this is one of these integrals where you do integration by parts twice, and that allows you to write the integral in terms of itself, and then you solve for the integral. So let me call this integral I. So what we showed is that I, up here, is equal to, we showed that it equals this, and let me maybe simplify that. So this I just carried right down. This, I just distributed the b over a to this. And this, I pulled out negative b over a. So that was a constant. That got multiplied by another negative b over a. So I've got negative b squared over a squared. And then, but other than that, other than these constants that got put together to get that, what I have is I have the integral of e to the ax sine bx, which is I. So I just write, I summarize what happened with the constants, which was a negative b squared over a squared, and then I just write I. And now I solve this for I. So I'm going to move this over to the left. And if I get a common denominator, because I'm doing I plus b squared over a squared I, if I collect that, I'm going to get this, which is some simple algebra there. And that would equal this, because this is just carried right down. And then finally, I solve for I. To solve for I would multiply by the reciprocal of this. And again, it's just a little bit of algebra, but this is what I get for I. Now, there's something a little bit funny happening here, which is typically, you know, we're looking for all antiderivatives, so usually we're used to having a plus c at the end. Technically, I just found one antiderivative, so if I wanted to find all antiderivatives, I would write that plus c. Anyway, to make a long story short, or I guess I have, at this point, I failed miserably at making it short, but we're just going to take this answer and use it. We were here. This is an improper integral, so I'll do the limit as b goes to infinity. I'll write the antiderivative of this thing, and let's not get confused about the letter b here, because, yeah, unfortunately, when I wrote this, I was using the letter b, but this won't really cause any confusion because we're going to replace b, because really this b, for us, we were using the letter k, so all of those b's are going to turn into k's, and then that's not the same as this b, but it won't confuse us because they'll be k's. So basically, I'm looking at this, except instead of a, I have negative s, and instead of b, I have k. So I am going to write this answer down, and once again, instead of a, I have negative s, and instead of b, I have k. So, negative s sine kt, because instead of x, I have t, right? So that's this, and then I have negative k cosine kt. This is in parentheses times e to the negative st. On the bottom, I've got a squared plus b squared, so that's negative s squared is just s squared, so I've got s squared plus k squared on the bottom. And this, I put in 0 and b, and those values go in for t. So this is the limit as b goes to infinity of, let's see, negative s sine kb minus k cosine kb e to the negative sb, or s squared plus k squared, minus, and let me put this in parentheses so I don't forget to distribute anything, I'm going to put in 0 for t. But let me try to be smart about this. Sine of 0 is 0, so I like that. Cosine of 0 is 1, so here I'm going to have a negative k. E to the 0 is 1, so this is just negative k times 1. There we go, so that wasn't so bad. Okay, now we're basically done. Once again, actually, if I keep track of where I am and the formula that I'm trying to derive, it looks like the answer that I want is right here, meaning hopefully this limit is 0. But it is, actually. This is, if you'll allow me, this isn't too hard to see that this goes to 0. So once again, b is going to infinity, s and k and everything else is all just constants, and s is a positive number. B is the one going to infinity. This stuff in parentheses is all just periodic functions, these sines and cosines. And I mean like periodic bounded functions. Sine and cosine is always between -1 and 1. So this stuff in parentheses is always at most some specific number, like this could be at most s, because like if it was s times -1, that's the biggest it could be. This could be at most k, because if it was k times -1, that's the biggest cosine could ever be. So this stuff in parentheses is at most a constant. It's getting multiplied by something that's going to 0. Right? So here I have something that is not very big, and it's getting multiplied by something that's going to 0. The denominator is literally just a constant, because the variable here is b. b is going to infinity. By the way, this s looks terrible. So this part does go to 0, and we just get this part. All right, good. So hopefully you believe enough that the table is accurate. We checked 3 entries at this point. Now let me go over some basic theory of these that's in the book, like, yeah, so, yeah, there's linearity of the Laplace transform, which makes sense. This is, and this is a commonality between Laplace transforms and derivatives and integrals. When you're doing the derivative of, say, a constant times a function, you just leave the constant right there. And if you are doing the same thing for an integral of a constant times a function, you can just pull the constant out. You can do that with Laplace transforms as well. So if you have if you're trying to do the Laplace transform of a f of t plus b g of t, you can just do a times the Laplace transform of f plus b times the Laplace transform of g. There's also mathematical questions about whether these things exist, like do Laplace transforms exist? And without getting too deep into it, the answer is, as far as we're concerned, yes. More specifically, there is Theorem 2 in the book, which basically says that if f is piecewise continuous and of exponential order, meaning that the rate of growth is at most exponential, roughly speaking. Exponential functions grow really fast, and most of the functions that we talk about in this class don't grow any faster than exponential. So this is a theorem that, as far as we're concerned, we're not going to have to worry about this too much. The Laplace transforms of the functions that we're interested in do exist, for sure. Yeah. There is also the uniqueness of a Laplace transform, which is Theorem 3. This, roughly speaking, says that as long as we're talking about two functions f and g that have Laplace transforms, according to Theorem 2, if their Laplace transforms are the same, like if big F and big G are the same, then the two original functions, little f and little g, must have also been the same. This allows us to take inverse Laplace transforms, meaning if I tell you the Laplace transform of a function and ask you what the original function was, you can tell me. This theorem is telling us that there's only one possibility for what the original function could have been, because you can't have two original functions with the same Laplace transform, at least under nice conditions, and the functions that we're going to be talking about are all of exponential order at most. So this applies to all of the ones that we're going to talk about. So, okay, so that was some real quick and real light theory of Laplace transforms. But let me bring this back to the real world, or yeah, maybe more real world, by finding, say, the Laplace transform of this. And I'm just going to use the table and use what we know. So, what do I know? I know that I can break this sum up and just do the Laplace transform of this one plus the Laplace transform of this one plus the Laplace transform of this one. Why is this so... Why are you having so much trouble focusing? Okay. Well, we found the Laplace transform of sine kt. That was here. So this one is going to be, so it's k over s squared plus k squared, so it's going to be 3 over s squared plus 9. That's this one. We also found the Laplace transform of t. The Laplace transform of t was 1 over s squared. The Laplace transform of 2t is just going to be 2 over s squared. We also, and I guess we did not do this one, but it is in the table, and I'm encouraging you to just use the table from now on. The Laplace transform of e to the at is 1 over s minus a. So this should be 3 over s minus 7, because if the 3 weren't there, it would just be 1 over s minus 7. And that's what we do with constant multiples, is the 3 just carries right down. Yeah, so this is actually really easy. It's just looking things up in the table, or remembering them, and putting them together for the example. Let's do our first inverse Laplace transform. This is not too hard. It's basically just using the same table, except I'm looking for things, you know, I'm looking to recognize something in this column, and then the answer that I'm going to write is whatever corresponds in this column. So, let's see. I've got a 2 over s. Well, in the table, I do see 1 over s. So the inverse Laplace transform of 1 over s would just be 1. So the inverse Laplace transform of 2 over s would just be 2. Because again, that's how we do constant multiples. Now, let's see here. I've got a 7 over s to the 4th. The way that I get powers of s is like this rule. So this is telling me, let's see, I want to have s to the 4th on the bottom, so maybe n is 3. So this is telling me that, yeah, so maybe I'm not going to need this space, so we'll just write some scratch work here. the Laplace transform of t cubed, according to this rule, would be 3 factorial, so 6 over s to the 4th, right? I would like negative 7 over s to the 4th. So probably the way to fix this is to write like negative 7/6 t cubed, right? Because, once again, the Laplace transform of this would be 6 over s to the 4th. The 6's would cancel, and I would get negative 7 over s to the 4th. Okay, now I have this part, 1 over s to the 4th plus 4. This looks like, so I have s squared plus a number in the denominator, and that looks like either this or this. If I look back, I don't have any s's in the numerator, I just have a constant in the numerator. So now I'm thinking it's more like this. The sine, not the cosine. Cosine has s's in the numerator, so I'm looking at the sine. Now, it seems to me that k should probably be 2 because I'm looking at s squared plus 4, and so that k squared is 4. Unfortunately, I don't have a 2 on the top. Like it doesn't look exactly like this. But I can fix that. I can say 1/2 sine of 2t, right? Because the Laplace transform of sine of 2t would have it would be 2 over s squared plus 4, but then that 2 would cancel this 2, and I would get 1 over s squared plus 4, right? So hopefully that made sense. There's a lot of, because of the way this works, because you can just pull constants in and out this way, there's a lot of this type of business that's familiar to us when we do integrals, where you have to fix a constant, and that often ends up with you having to divide by a constant in order to cancel something out. So it's the same type of skills that you've been learning when you've done derivatives and integrals. It's just that the Laplace transforms are a new operation that you can do to a function to get another type of function. But many of the same rules apply. Okay, so I'm going to upload this, and next time we will actually learn how to solve a differential equation using Laplace transforms, because I will not get to that today.